For generations, black holes have been portrayed as the universe's ultimate destroyers. Regions of space where gravity is so intense that nothing, not even light, can escape. They consume gas, dust, and even stars, leaving behind only darkness. But modern astronomy continues to reveal that the universe is far more complex than those simple descriptions suggest. The James Webb Space Telescope, built to explore the earliest chapters of cosmic history, is transforming our understanding of these mysterious objects. With its powerful infrared instruments, Webb can peer through enormous clouds of dust that hide some of the most energetic events in the universe. Among its many discoveries is a remarkable object that has attracted worldwide attention. Astronomers have identified evidence of a supermassive black hole moving through space after being displaced from its original galaxy. Rather than remaining quietly at the center of its host galaxy, where most supermassive black holes are found, this one appears to be traveling at extraordinary speed. How could something so massive be set in motion? One leading explanation involves a dramatic collision between galaxies. When two galaxies merge, their central black holes eventually spiral toward one another. If a third black hole later joins the system, or if the final merger releases gravitational waves unevenly, the newly combined black hole can receive an enormous kick, sending it racing through intergalactic space. Although this sounds extraordinary, it follows the predictions of Einstein's theory of general relativity. What surprised researchers even more was what appeared behind the moving black hole. Instead of leaving only destruction, observations suggest that its passage may compress enormous clouds of gas. As these clouds become denser, gravity can take over, allowing new generations of stars to begin forming. In other words, the black hole may indirectly trigger star birth. This doesn't mean the black hole is creating stars itself. Rather, its motion changes the surrounding environment, producing conditions where star formation becomes possible. If confirmed, this process demonstrates that black holes can influence galaxies in more ways than scientists previously appreciated. They are not merely cosmic vacuum cleaners. They can also shape the evolution of galaxies across millions of years. Researchers combined observations from multiple observatories to investigate the object in greater detail. Webb's infrared vision helped reveal structures hidden behind dust, while earlier observations from other space telescopes provided valuable supporting evidence. Together, these datasets painted the picture of a rare and fascinating cosmic event. The apparent trail extends across an enormous distance, far larger than our own Milky Way, making it one of the most striking structures associated with a runaway black hole. Even so, astronomers remain cautious. Science advances by testing ideas repeatedly. Alternative explanations continue to be investigated, and additional observations will determine whether the interpretation holds up under closer examination. That careful approach is one reason discoveries made with the James Webb Space Telescope carry so much scientific importance. Rather than rushing toward dramatic conclusions, researchers compare observations, challenge their own hypotheses, and search for independent confirmation. Every unexpected discovery teaches us something new about how the universe works. Sometimes those lessons strengthen existing theories. Other times, they reveal processes no one had previously imagined. If this remarkable black hole truly is helping trigger star formation while speeding through space, it would become another reminder that the universe rarely behaves in the simple ways we expect. And this extraordinary discovery is only the beginning. Elsewhere, Webb has captured one of the most spectacular galactic collisions ever observed, revealing enormous clouds of dust, intense bursts of star formation, and clues to how giant galaxies evolve over billions of years. While astronomers continued studying the runaway black hole, the James Webb Space Telescope turned its attention to another extraordinary region of the universe, a pair of galaxies caught in the final stages of a colossal collision. Known as ARP 220, This system lies hundreds of millions of light-years from Earth and is one of the brightest infrared galaxies ever discovered. Although it appears calm through ordinary telescopes, Webb's infrared vision reveals a completely different scene hidden beneath enormous clouds of dust. Deep inside the merger, two galactic cores continue their slow dance toward becoming a single giant galaxy. Around them, vast clouds of gas collapse under gravity, producing one of the most intense bursts of star formation ever observed. Thousands of massive young stars illuminate the surrounding dust, creating spectacular structures that are invisible in ordinary visible light. For astronomers, systems like ARP 220 serve as natural laboratories. By observing galaxies in the middle of a merger, researchers can understand how similar events shaped the Milky Way billions of years ago. Every new image reveals details about how gravity redistributes gas, triggers star formation, and feeds the enormous black holes hidden within galactic centers. Yet Webb's discoveries extend far beyond nearby galaxies. One of its greatest achievements has been detecting galaxies that formed when the universe was still remarkably young. Their light has traveled for more than 13 billion years before finally reaching the telescope, allowing scientists to observe cosmic history almost from the beginning. Some of these distant galaxies appear brighter and more evolved than many early models predicted. That does not mean current theories have been overturned. Instead, it suggests that galaxy formation in the early universe may have been more rapid and more efficient than astronomers once expected. Researchers continue refining computer simulations to determine how these surprisingly mature galaxies formed so soon after the Big Bang. Every observation helps improve our understanding of the universe's earliest generations of stars. Webb accomplishes this by detecting infrared light that has been stretched by the expansion of space over billions of years. Signals that originally left young galaxies as visible light now arrive at Earth in infrared wavelengths, making Webb uniquely suited to study the ancient cosmos. This ability allows astronomers to investigate questions that remained impossible only a few years ago. How quickly did the first galaxies assemble? When did the earliest supermassive black holes appear? How did the first generations of stars enrich the universe with the elements needed to form planets, and eventually life? These questions remain among the greatest challenges in modern astronomy. Each new observing campaign produces discoveries that refine our understanding while raising entirely new mysteries. That is the true power of the James Webb Space Telescope. It was not built simply to capture beautiful images. It was designed to answer some of humanity's deepest questions about where galaxies come from, how black holes evolve, and how the universe transformed from a nearly uniform sea of hydrogen into the richly structured cosmos we see today. The discoveries are still unfolding. Future observations will revisit many of these remarkable objects using longer exposure times and additional instruments, allowing scientists to test current interpretations and search for details that remain hidden today. As Webb continues its mission, one thing has become increasingly clear. The universe is proving to be more dynamic, more complex, and more surprising than anyone imagined. Every distant galaxy, every hidden black hole, and every ancient beam of light adds another piece to the story of our cosmic origins. And with every new observation, humanity takes another step toward understanding the extraordinary universe we call home.